campus, Telangana. Sir has awarded his PhD in NIT Warangal and postdoc in Belgium. Sir has published more than 85 journal research articles, 2 books, and Sir has more than 25 years of teaching experience. And the research area includes biofluid dynamics, and Sir has research interest in fluid dynamics, biomechanics. Total 7 students has completed their PhD degree under the guidance of Sir, and 3 are working under the guidance of Dr. K. Maruti Prasad Sir. Sir has awarded Adarsh Vidya Saraswati Rashtriya Puraskar by Global Management Council, Gujarat, India in 2019. Best Research Award by Geetam Deemed to be University in 2018. Best Teacher Award by Kamala Institute of Technology and Science in 2008. Sir has completed 2 projects, and Sir also visited abroad for the invited talks. Sir has visited China, Hong Kong, Singapore, Kuwait, etc. With this brief introduction, I request Dr. K. Maruti Prasad Sir to chair the session.
So am I audible now?
Yes, sir.
Yeah, sorry, I think mic was off. Now I am inviting Dr. Mintu Ratan, Assistant Professor, Punjab University, Chandigarh, to give a talk on solid mechanics. So now I am requesting Mintu Ratan sir, please start the session. Thank you, sir.
Thank you, sir. Thank you, Maruti Prasad. I would like to thank you. Yes, Priyanka ma'am, I have already sent the video. Please play it.
Okay, sir.
So that we don't have any disturbance.
Okay.
Okay, thank you. It is a matter of great pleasure that Department of Mathematics of Karnatak University, in collaboration with Private Institute of Mathematical Sciences, it is a matter of great pleasure that Department of Mathematics of Karnatak University, in collaboration with Private Institute of Mathematical Sciences and Dharwad Regional Science Center, is organizing an international conference on mathematical analysis and its applications. To conduct a conference in the area of mathematics, which is attracting academic participation nationally and internationally, is truly an achievement. I appreciate the progress of the department and wish it well on its onward journey of excellence. I am thankful to the organizers of the conference and conference chair, Professor S.C. Sharla Shetty, who has given me the chance to participate in this conference. This is the outline of my talk. I am going to start with the introduction of mathematical modeling, creep, and composite materials. Then I will come to steady-state creep of composite rotating disk problem. Let's talk about what is mathematical modeling, creep, and composite. Much of our progress in the last few centuries has made it necessary to apply mathematical methods to real-life problems arising from different fields. The use of mathematics in solving real-world problems has become widespread, especially due to increasing computational powers of digital computers and computing methods, both of which have facilitated the handling of lengthy and complicated problems. The process of translation of a real-life problem into a mathematical form can give a better representation and solution of certain problems. This process of translation is called mathematical modeling. For modeling, the first step is to understand the problem and to find the relevant factors or essential parameters involved in the problem. The next step is to find an equation or an inequality or a geometric figure using the parameters already identified. Then, to find the solution, one has to do some operation which involves solving an equation, calculations, or applying methods or theorems already known. Many times model equations are obtained by assuming a situation in an idealized context. The model will be useful if it explains all the facts that one would like to explain. Otherwise, one will reject it or else it is a matter of great pleasure that Department of Mathematics of Karnatak University, in collaboration with Private Institute of Mathematical Sciences and Dharwad Regional Science Center, is organizing an international conference on mathematical analysis and its applications. To conduct a conference in the area of mathematics, which is attracting academic participation nationally and internationally, is truly an achievement. I appreciate the progress of the department and wish it well on its onward journey of excellence. I am thankful to the organizers of the conference and conference chair, Professor S.C. Sharla Shetty, who has given me the chance to participate in this conference. This is the outline of my talk. I am going to start with the introduction of mathematical modeling, creep, and composite materials. Then I will come to steady state creep of composite rotating disk problem. Let's talk about what is mathematical modeling, creep and composite. Much of our progress in the last few centuries has made it necessary to apply mathematical methods to real-life problems arising from different fields. The use of mathematics in solving real-world problems has become widespread, especially due to increasing computational powers of digital computers and computing methods, both of which have facilitated the handling of lengthy and complicated problems. The process of translation of a real-life problem into a mathematical form can give a better representation and solution of certain problems. This process of translation is called mathematical modeling. For modeling, the first step is to understand the problem and to find the relevant factors or essential parameters involved in the problem. The next step is to find an equation or an inequality or a geometric figure using the parameters already identified. Then, to find the solution, one has to do some operation which involves solving an equation, calculations, or applying methods or theorems already known. Many times model equations are obtained by assuming a situation in an idealized context. The model will be useful if it explains all the facts that one would like to explain. Otherwise, one will reject it or else improve it, then test it again. Under many service conditions, materials are required to sustain steady loads for a long period of time and under different temperature conditions. Example, furnace parts, blades of turbine rotors, timber beams in the roof of the buildings, filaments in vacuum tubes, etc. Under these conditions, material may continue to deform until its usefulness is seriously impaired. Such time-dependent deformations can grow large and result in fracture of the member without any increase in load. This time-dependent strain occurring under constant stress is known as creep. Creep may be defined as the process by which plastic flow occurs when a constant stress is applied for a prolonged period of time. Creep can take place and lead to fracture at static stresses much smaller than those which will break the specimen when loaded quickly. Synthetic ropes will elongate when loaded over a long period of time. This time-dependent strain occurring under constant stress is known as creep. Probably, the first recognition given to the industrial importance of creep was by Dickinson in 1922 when he published his research on the creep resistance of structural steel and alloy steel members in a furnace. When metal-metallic composites are tested under creep conditions using tensile or shear configurations, it is usually possible to identify the standard three distinct stages of flow within the creep curve. One is primary creep, the other is secondary creep, and the third one is tertiary creep. A creep curve is a plot between the total creep and the time for the entire duration of test. There is generally a normal primary stage known as transient creep, in which the strain rate decreases with increasing time. And this is followed by a brief secondary stage where the strain rate remains reasonably constant. This stage is now also known as steady state creep. and then an extended tertiary stage where the strain rate increases with time until fracture occurs. Figure shows a creep curve and marks the various stages of creep. Although it was recognized that the secondary stage was very short by comparison with most pure metals and solid solution alloys. By contrast, some metal metric composites exhibit creep curves where the secondary stage was more linearly delineated. The close similarities in the creep curves of unreinforced powder metallurgy materials and metal metric composites provides support for analytical or theoretical treatments of the creep results for metal metric composites in terms of the steady state creep rates. Many engineering applications provide severe thermomechanical loading because of simultaneous presence of high thermal gradients and loads where the conventional materials like metals or ceramics alone may not be suitable. Very high loads or high temperature will accelerate the creep process. The combination of these three factors, load, temperature, and time, determines whether creep is relevant for a particular problem or not. The growth of technology has placed rather severe demands on material engineers to come up with novel materials at low cost to meet stringent and often contradictory property requirements which conventional materials cannot satisfy. In this respect, composite materials show great promise. These are the materials which are tailored by combining two or more materials to get properties that are not attainable by any of its constituent alone. Let's take a closer look at its structure. It has at least two different materials whose properties complement each other. These materials contain either dispersed fibers, particles, or whiskers embedded in a matrix, which may be metallic, polymer, or a ceramic material. Metal matrix composites are based on metals or metal alloys reinforced with fibers, particles, or whiskers. Metal metric composites containing particles and whiskers are generally isotopic and are relatively cheap. The composites might contain aligned, continuous, aligned discontinuous, or random fibers, particles or whiskers of ceramic materials like silicon carbide, alumina, etc. in a matrix which may be a metal or an alloy. Because of their superior stiffness, high strength at elevated temperatures, and better creep characteristics, metal metric composites are finding increasing applications in components exposed to elevated temperatures. Thus, composite material is a combination of two or more micro-constituents differing in the form and are essentially insoluble in each other. They are different from alloys. Two or more materials with different physical and chemical properties are combined to create a specialized material required to do a particular job. They improve the properties of their base materials and are applicable in many situations. The concept of functionally graded materials emerged and led to the development of superior heat-resistant materials while keeping the cost under control. FGMs are special types of composites containing inhomogeneous distribution of constituents like heat-resistant ceramics on the higher temperature side and tough metals with high thermal conductivity on the lower temperature side, so designed to withstand severe thermomechanical loading. These materials have been developed as ultra-high temperature resistance materials for potential applications in aircrafts, space vehicles, and other products working at elevated temperatures. In addition to excellent mechanical and thermal properties, FGMs also possess the advantage of optimizing the use of costly dispersoids, as the composition of dispersoids in FGMs changes from the high temperature region to the low temperature region. Mechanical properties of composite depend substantially on the processing and fabrication methods used, as well as on the fiber orientation. Safety and efficiency are non-negotiable in modern shipping. The number one choice for mooring lines is Dyneema company. Fibers from Dyneema have been proven to have lowest creep rate and longest lifetime. Now let's start with the steady state creep of composite rotating disc. Rotating disc is a commonly encountered component in aero engines, automobiles, turbines, pumps, compressors, flywheels, and in a number of other dynamic applications. Many of these applications are exposed to elevated temperatures where creep deformation becomes important. The enhanced creep of lightweight aluminium and its alloys may not permit their application at elevated temperatures. From this point of view, components based on metal matrix composites with aluminium or aluminium alloys reinforced with ceramic, fibers, whiskers, putty plates are found to be extremely useful. Experimental studies have demonstrated that steady-state creep rate in aluminium or its alloys may be reduced by several orders of magnitude when it is reinforced with ceramic particles or whiskers like silicon carbide. Any research work on composites should therefore attempt to analyze creep in structural components like rotating disc made of lightweight aluminium, ceramic, composite, so as to develop more reliable design codes for real-life applications. Creep is of extreme technological significance since it limits the use of modern materials in a number of applications such as automotive, engines, and components of aerospace and power generation plants. Superior mechanical properties and high strength to weight ratio of such materials have led to an increased interest in the automobile and aerospace industries, in which saving the weight of component is a critical issue. The prediction and analysis of creep properties to assess service life of engineering components made of composites is of great help for practicing engineers. Several fabrication techniques have been developed in recent years to manufacture the composites with specific properties in mind. The aluminium matrix can be reinforced with a variety of ceramic particles of different shapes and sizes to achieve the desired properties. This motivates us to do work on steady-state creep of a rotating disc. Let us consider an annular disc of aluminium matrix reinforced with silicon carbide putty plates having inner radius A and outer radius B. The putty plate size of the material is denoted by P, and the volume fraction V of the reinforcement is considered to be 10 volume percent fraction of the constituent material. The density variation in the composite is expressed by the law of mixture formula, where ρm is the density of the matrix alloy and ρd represents the density of the dispersed silicon carbide particles. For the present study, the disk with 3 temperature profiles have been considered. Disk with uniform temperature profile D100 is operating at uniform temperature of 623 Kelvin along the radial distance. Disk with linearly decreasing thermal gradient profile are represented by D101, and 3 disks have been operating at linearly decreasing thermal gradients having temperature distribution TR denoted by A minus BR, where A and B can be calculated by using the values of inner radius, outer radius, and temperature and inner radius and outer radius of the disk. For nonlinear profile, 3 disks D102 operating under parabolically decreasing temperature distribution TR have been used, where TR is given by C minus D R square, where C and D as usual can be calculated using the values of inner radius, outer radius, temperature at inner radius, and temperature at outer radius. For various composite disks under various thermal gradation profiles, the values of TA and TB for this are given in this table. We can take the values according to this table for uniform, linear, and non-linear composite disks. The steady state creep response of the aluminum silicon carbide particulate composite has been described by Sherby's constitutive model, which gives the relation between the strain rate, effective stress, threshold stress, and creep parameter. Effective strain rate under biaxial stress is noted by epsilon bar dot. Effective stress under biaxial stress is denoted by sigma bar. Threshold stress is denoted by sigma naught, and creep parameter by M. In a particle reinforced composite, the creep parameters M and sigma naught depend on the particle size P and the particle content V apart from the temperature T. The creep parameters M and sigma naught have been obtained from the creep results reported by Pandey in 1992 for aluminum silicon carbide composite under uniaxial loading. The values of the creep parameters M and sigma naught as function of material parameters P, V, and T have been calculated through software data fit using following regression equations. For symmetry considerations, principal stresses are taken along radial, tangential, and axial directions for the composite disk having uniform thickness h, rotating with angular velocity omega. For the purpose of modeling, we assume that steady state condition of stress. We assume that elastic deformations are small for the disk and can be neglected as compared to the creep deformations. We also assume the biaxial state of stress exists at any point of the disk. Taking reference frame along the radial, tangential, and axial directions, the generalized relation for the creep in isotropic rotating disk is given by radial strain rate, tangential strain rate, and axial strain rate in terms of effective strain rate, effective stress, radial stress, tangential stress, and axial stress, where the effective stress is calculated using von Mises yield criteria as given in the formula. For biaxial state of stress, axial stress can be neglected and the effective stress is given in terms of radial and tangential stresses only. Further, substituting the value of effective strain rate from Sherby's constitutive model in the generalized constitutive equations, we get the following constitutive equations in terms of effective stress, threshold stress, and X, where X is the ratio of radial to tangential stress, and here UR is the radial displacement. Equation 16 and 17 for radial and tangential strain rate from previous constitutive equations can be solved to obtain tangential stress sigma theta in terms of radial displacement rate at A, parameter M, psi 1 and psi 2, where radial displacement rate at A can be calculated using the given formula in terms of psi 1 and psi 2, where psi 1 and psi 2 can be further calculated using psi and sigma naught, where psi can be calculated using phi as given in the expression, and phi can be calculated using 2x minus 1 divided by 2 minus x, where x represents the ratio of radial stress to tangential stress. The equation of motion for a rotating disk of uniform thickness h may be obtained by considering the equilibrium of an element in the composite disk confined between radial distance r and r plus dr and an interval of angle between theta and theta plus d theta. The equilibrium of forces in the radial direction of the element under assumed conditions gives the following equation of equilibrium. Knowing the tangential stress distribution sigma theta from the previous equation, values of sigma r, that is radial strain along the radius, can be obtained using the given formula. Thus, knowing the values of radial and tangential stresses, we can calculate the radial, tangential and axial strain rates from the constitutive relations already given by equation number 16, 17, 18 respectively. An iterative solution technique can be employed using the boundary conditions that radial stresses at inner and outer boundaries should be zero. The stress distributions is evaluated from the above analysis by iterative numerical scheme of computations. The iterations are continued till the process converges, yield the values of stress at different points of the radius grid. For rapid convergence, 75% of the value of tangential stress obtained in the current iteration has been mixed with 25% of the value of tangential stress obtained in the last iteration for the use in the next iteration as shown. Numerical computation has been done to obtain the steady state creep response of the disks having particle size P equal to 1.7 micrometer and particle content V equal to 10 volume percent of the aluminum silicon carbide particulate. In order to validate the developed computer program, the results for our rotating steel disk were obtained and compared with the available experimental results of Wall, which performed the experiment in 1954 for the same type of disk and operating under same conditions, as mentioned in the table. The comparison of present theoretical work and Wall's experimental work done in 1954 for strain rates versus radial distance is shown graphically in the given figure. This graph depicts that there is a good agreement between the present theoretical work and Wall's experimental results for radial strain rates versus radial distance. The tangential strain rates also follow the same trends for present work as well as Wahl's experimental results throughout the radial distance. A good agreement and similar trends observed between the present theoretical and Wahl's experiment strain rates inspire the confidence in us. Based on the above mathematical formulation, a computer code in MATLAB has been generated to calculate the steady state free behavior of the disk subjected to uniform, linear, and non-linear thermal gradation. Results are compared graphically to study the effect of thermal gradient at elevated temperatures. Figure shows the variation of radial stress, tangential stress, radial strain rates, and tangential strain rates along radial distance in the disk with uniform profile, linear and non-linear profiles having temperature gradient of 0 Kelvin, 24.63 Kelvin, and 30 Kelvin. We can see clearly from the figure A that as one moves radially outwards from inner radius, the radial stress increases from 0, reaches a maximum value near the middle of the disk, and then decreases to 0 towards the outer radii for all the above said disks. The value of radial stresses for disk D100 having uniform temperature along the radius shows very minor reduction as compared to this D101 and 102 having decreasing linear and non-linear temperature gradation respectively. Further, effect of different temperature profile on tangential stresses as shown in the figure D is very small. The graph shows that the tangential stresses increases from inner radius, attain maximum values, and then decreases as one approaches outer radius. The tangential stresses is lowest for disk D100 with uniform profile and highest for disk D102 with non-uniform profile as compared to other disks. From the figure C, we can see that with the change in temperature distribution, the radial strain rate is affected significantly. So, this with linear and non-linear profiles, the radial strain rate decreases near the inner radius and increases near the outer radius in comparison to this with uniform profile. Similarly, the tangential strain rates are also significantly affected with the change in temperature profile of the disk. Figure D clearly shows that the tangential strain rate decreases for disks with uniform, linear and non-linear profile as one moves from inner to outer radius. At the inner radius, the tangential strain rate has lowest value for disk with uniform profile in comparison to rest of the disk. And at the outer radius, the strain rate has lowest value for disk with non-uniform profile. Similarly, as shown in figure 3, we get the similar trends as already discussed in figure 2 for variation of radial stress, tangential stress, radial strain rate, and tangential strain rate along the radial distance in disks with uniform, linear and non-linear profiles having temperature gradient of 0 Kelvin, 49.25 Kelvin, and 60 Kelvin. Further, disks with temperature gradient of 0 Kelvin, 73.87 Kelvin, and 90 Kelvin also shows the same trends as already discussed in figure 2 and 3 for radial as well as tangential stresses and strain rates. The effect of different linear thermal gradients on radial, tangential stresses and radial and tangential strain rates developed in rotating disk having temperature gradient of 73.63 Kelvin, 49.25 Kelvin, and 73.87 Kelvin, respectively, are shown in this figure. The effect of different temperature thermal gradients on radial stresses developed in a rotating disk having temperature gradient of 23.63 Kelvin, 49.23 Kelvin, and 73.87 Kelvin, respectively, as shown in figure A, is very, very small. And the effect of different thermal gradient on tangential stresses, as shown in figure B, is also very small. The effect of different linear thermal gradients on radial strain rates can be seen near the inner and outer radii of the disk from the graph. And the similar trends for tangential strain rates can be seen from the graph near the inner and outer radii for the effect of different linear thermal gradients. As already discussed in figure 5, similar kind of variations of radial stress, tangential stress, radial strain rates, and tangential strain rates along radial distance in disk with non-uniform profiles having temperature gradient of 30 Kelvin, 60 Kelvin, and 90 Kelvin can be seen from the graph. As seen from the graphs, the strain rates are significantly affected with change in thermal gradient of the disk. So, the study of thermal gradient in rotating disks will give new insights to material engineers and designers. A significant improvement in specific strength and stiffness may be attained in these composites using variations in functionally gradient materials. Rotating disk is a commonly encountered component in aero engines, automobiles, turbines, pumps, compressors, flywheels, and in a number of other dynamic applications. Many of these applications are exposed to elevated temperatures where creep deformations become important. The enhanced creep of lightweight aluminum and its alloy may not permit their applications at elevated temperature. From this point of view, any research work on composites should therefore attempt to analyze creep in structural components like rotating disks made of lightweight aluminum ceramic composites so as to develop more reliable design codes for real-life application. I would like to thank the audience for their kind patience, and once again I am thankful to the organizers of the conference.
Hello. Hello, sir. Dr. Mintu Ratan, sir. Is my voice audible? Yes, sir. We have a Dr. Maruti Prasad, sir, as a session, sir.
Sir, there's a good explanation from the solid mechanics side. If any audience is having any doubts, I think it is clear, sir. From my side, I think there is no questions because the lecture will clarify all my doubts and everything. Thank you for your nice presentation, sir. Noise is coming. Hello? Hello? Ratanji? So much of noise is coming from your side, I think. I don't know the reason, but it's a nice presentation, sir. Yes, sir. It is audible. It's a very nice presentation about the solid mechanics, sir. We come to know the rotating springs and composite discs and other things. It's a very nice talk. So thank you for your innovative talk on this topic, sir. Thank you. Yes, sir. Thank you, sir. Thank you, because a lot of noise. Dr. Dhananjay, am I audible, sir?
Yes, sir. Yes, sir. Mr. Burma, you are audible.
Yeah. Sir, this is Professor Maruti Prasad from Geetam University. Now I am inviting Dr. Dhananjaya, Associate Professor of BITS Pilani, Goa, to give a talk on computational partial differential equations and numerical analysis. I am inviting you, sir, to start your session, sir.
Okay.
Dhananjay, sir?
Yes, sir. I will share this.
Yeah, thank you, sir.
My slide is good. My slides are visible or not?
Yes, sir, it is visible.
Okay. Can I start?
Yes, sir, you can start, sir. Please continue.
So I thank you for Shiva Sukhi sir for giving me the wonderful opportunity. And this is a hard work with the PhD student. And the collaborator was a great variator. I think I want to be clearly audible. My voice is clear?
Yes, sir.
So my title of the talk is the organized location methods for probability problems with interface.
It's not clear.
So my second talk as follows.
Dhananjay, sir, your voice, some disturbance is there.
Yes. Question marks. So I'll start.
No problem, sir. You start. Yeah, thank you.
So talk as follows. I will do brief introduction of the interface terms. Then I will go to one-dimensional parabolic problem with interfaces. Then we will the current request from orthogonal and location approximation. then show some numerical experiments. So after discussing 1D parabolic, then I will move to 2D parabolic interface problems. Then we apply the overall point mechanism, other sign collocation approximation. So then we will also talk about some numerical experiments. Then I will conclude my talk, then I will show some references. So deriving accurate, efficient numerical solutions to interface problems is not a trivial task. So the major difficulties arise from two factors. The first one is the standard numerical method, like finite difference method, finite annual method, finite volume methods, and so on. Without treating the interface zone conditions carefully, perform poorly or lower rate of accuracy that we miss, or even fail to converge. So when you want to solve interface problems, you will have to be very. So due to the fact that the physical solution is usually non-stuck or even discontinuous across the interface. The second difficulty arises incorporating interface conditions across the interface and incorporating boundary conditions, it is a challenge. Because of these two major difficulties, the traditional numerical methods applying interface problems as it is, one may have different challenges. And we're talking about one-dimensional parametric interface problem. We consider one-dimensional parabolic problem. As follows: this is the derivative minus of beta of x into mu x. This is the derivative of x. Okay, with respect to x is equal to f of x over t. So x is x domain is 0, capital A, t belongs to closing to 0, capital T. So here, so this beta of x, it takes beta 1 of x in this interval, whereas beta 2 of x in this interval. X belongs to local interval L, capital. So your x is equal to 0 and x is equal to capital L. So we are deriving this is N. Okay? So we are dividing into number of subintervals. So this is our interface. So then I can say this is x. So after this, you have beta 1 of x, from here onwards, you have beta 2 of x. Subject to the initial condition is u at x over 0 is equal to u of x. So u is a given function. And we consider a more general set of boundary conditions. So it covers all types of boundary conditions, definite, non-one, or boundary conditions. So mu naught u of 0, t minus mu naught boundary the mu x is 0, t is equal to 0, t. Similarly, you have another boundary condition. So the function of beta, so we have seen here beta here, this one. The piecewise condition or piecewise inverse function. With a finite jump across the interface. So our interface is there in this interval. So as I mentioned here, so I have taken a similar interface here. It can be more than one interface. The interface is lies in the interior point, not of the body. My interface is always the interior. So I have taken for convenience only one interface, so one can allow other interface also, more than one also. But similar procedure we can extend to more than one interface. And these conditions shown here, so these are conditions, known conditions. These are known conditions. The other conditions that X is equal to XL are typically like this. So gamma 1 times U of XL minus gamma T is equal to gamma 2 times U of XL plus gamma T. So similarly, this is a flex interface condition. So we are placing it from this side. So the information is coming from this side, which is plus. This is information is coming from this side, which is minus plus. So this is my interface. So after this, okay, remaining after 3 times are fine. Only this is the interface. So some of the applications I can show you here. So go-into layer padding and co-into layer for micro machining and patterning. Temperature distribution in a double layer film, which is essential for precision for laser process. So example one, so we have extracting of the density of tumor cells in the brain of a patient. So here the diffusion coefficients in the gray and white matters are different. So non-homogeneity of brain, so that is the gray and white, so we can classify beta of X is equal to beta 1 in gray matter, beta in white matter. So there are many other applications including anticyclons. So there are some others study languages such problems, interface problems, but several methods. So Albright and his group, they applied here are the accurate difference potential methods for parabolic problems. And J Fan and W Dye, so they also applied a new higher accurate numerical method for solving grid connection problems in a double layer to the normal boundary condition. And here, in the literature, many others tried several methods, but they had a difficulty of incorporating interface conditions and boundary conditions. So now, we have shown bonus time collocation methods for the interface problems. The question comes, so although there are some existing methods like that, why do we require a new method? What is the importance? So new methods based on arguments from collocation, spatial distributions, specifics, etc. The other traditional methods. Some methods are final difference methods, final handling methods, and so on. So these collocation methods they provide is global approximations to the solution and its first derivatives. So another accuracy working for final difference methods. So in this method, the proposed method requires no evaluation or approximation of integrals. If you go for finding element methods, so we have to find a good formulation, then we have to, in the reformulation, then you get some integrals, then we have to evaluate integrals by using appropriate quantitative rules. There are several integrals you need to evaluate. But in this proposed method, so we are free from evaluation of the integers. The present method exhibits superconvergence phenomena. What it means superconvergence means the accuracy of the certain points is higher than accuracy that can be achieved globally. And one more advantage of the AFCM is boundary conditions of all types of boundary conditions of all types of interface conditions are you can handle easily in this method. For more information about the present method, the orthogonal slide collocation method, you can this is a survey paper. So do biology and G failure. So orthogonal slide collocation method, so partial differential equations you can have. So here is our collaborator, here is one of our co-authors. So now let's see the orthogonal slide collocation method. Since we have the time, we have the social domain 0, 0 to 1. So we divide into number of subintervals. So we have so this is x naught is 0. So here this is your xn, this is equal capital. So we divide this is so x1, this is x2, x3 up to so. So given our social domain, we split into number of grid points. So we denote interval 0 from n such that this is our xn, okay, this is our xn, this is interface. So this is the interface part. So the items are called subintervals. This is the step size. So we can treat as the uniform step size. So we ensure hi, okay, I use okay, this is my h. So assume we can have the points are equally spacing points. So this is the spatial domain in the time domain. So this is the step size in the time domain. Delta t is equal to capital T upon capital M, where m is a positive integer. So we can distinguish time domain in this fashion. So the set of iteration belongs to collocated points. So now we will collocate the equation at collocation points. So these are the grid points. So now my collocation points are like this. So these are collocation points. Each subinterval, so I will use the 2 collocation points. Okay, so x0 to x1, okay, I have 2 collocation points. Here this is my J1, so this is my J2. So the collocation points are we take the 2-point Gauss legendary quadrature points. This is a one collocation point, this is another collocation point. We only have 1, 2, 3 up to so on. So I am choosing 2-point Gaussian Gauss legendary quadrature point because so I have set 4-point accuracy. So I require a quadrature collocation points in such a way that captures the 4-point accuracy. So this 2-point Gauss legendary quadrature gives 4-point accuracy. So you can also go for 3-point, 4-point, 5-point up to so. 2-point you can achieve 4-point accuracy. So the collocation points are like this. So here you can see these are grid points, these are collocation points. These are grid points, so this is the collocation point. So on each time level, the approximate solution U1 is a cubic polynomial, and each subinterval of the partition rho is determined in the following. So on time level Tn, so satisfy the current equation of the inner side collocation equations. So this okay, U1 of j minus U1 minus 1 of j upon delta t, where j stands for collocation equation. Okay, the idea side is this one. The j belongs to capital G. And then the boundary conditions. Okay, boundary conditions. So here I have denoted a symbol n minus of So supersede n minus r. So that means, okay, this is v1 minus r of j is equal to 1 upon 2 v1 of j plus v1 minus 1 of j. And beta is, as we have seen earlier, so up to 1 comma 2 up to small n, so it is beta 1, and n plus 1 onwards it is beta 2. So now, so we have to approximate the solution. So here, this is the collocation equation. So the equation we collocated. So this is the collocation equation. So now we approximate the solution we will form. So u1 of x is equal to y1 minus 1 comma 1 supersede n plus x minus 1 into y1 minus 1 comma 2 n up to 1. So this is a cubic polynomial. It's a cubic polynomial. You know the P3 can be polynomial of degree of not 3. So the basic functions are 1 x, x4, x2. Which involves 4 unknowns here. So this is one unknown, this is the second unknown, third unknown, fourth unknown. So we need to find these 4 unknowns. So differentiating because here we have derivatives here ux, u so we differentiate. If you differentiate one time, so we get this expression. So if you differentiate it second time, we get this expression. But our unknowns are 4 unknowns are there, these are 4 unknowns. We need to find. And these expressions, this expression is actually the equation, the collocation equation. So we got into a system of equation of this form. So if you express the matrix form, so we come across a system of this form. So where the matrix is G, H as follows. Where G is equal to, this is the matrix, so the matrix, then H is the matrix of this form. So H is the matrix of this form. So this is called this matrix minus delta theta in this form. So now y minus 1 at nth level is this one. So j minus 1 at nth level is this. So now y is value 1 comma 2 up to so on in case 1, k is value 1 comma 2 up to so on here. So in total there are 2 collocation points as we are seeing. So this is x0 is 0 and xn is equal to 1. So this is interface point. So these are collocated points. So there are 2 collocation equations are there. We have 2 boundary conditions. One boundary condition is this side, this is one boundary, so another boundary the right hand side. So since u and u are continuous functions of x equal to xi, so whenever we have a difficulty only at interface, we have difficulty. So the other places is fine. We have only difficulty at interface. So now, at x is equal to x star, we are always going 1 to up to 1, n minus 1. Okay, our interface is here, this is xl. Not including xl here. And this is my xl minus 1. So this is my xl plus 1. They are continuous. Okay? So these are continuous equations. So we get y is equal to ci minus 1 plus di into j minus 1 at another level. So we have ci and di matrices are of this equivalent matrices. So also assume okay, these solution u and the fluxes are continuous. Assume okay, they are continuous at the interface. If the continuous interface, you get the continuity the interface conditions. This is the equation coming from the interface. So this CL and DL matrices to matrices. So now, here, this here is a non-similar matrix. You can see this is a non-similar matrix. You calculate so like this. So now CL turned up and the DL turned up, you have this matrix. So now the collocation equations along with the continuity equations, if you combine, you will get to almost black diagonal matrix. They say ABD matrix. ABD stands for almost black diagonal matrix in a system of 4 order. So the system is of this form. Its size is 4 cos 4 So this is a 4 cos 4 If n is equal to 100, you can see. If n is equal to 100, you will have 402 cos 402 matrix. It's a non-form matrix. So the structure of the matrix is almost diagonal matrix form. So this is this stands for this is the contribution from the left boundary. This stands for the contribution from the right boundary. And G1, H1, C1, D1, all these matrices, two matrices, and the ID stands for this is the identity matrix of two matrix. So you can see here, there is a color. So this is the contribution from the interface. So these two rows are coming from the interface conditions. So the rest of the matrices you can derive easily, but this you have to be careful. So for the size is the size of the system is very large. So if you go for finding this solution, it consumes a lot of memory from the system. So what we do is we will convert the system, a smaller system, then we go for solution. So now, how to convince the system? So now we show the process. So now this is the unknown. So these matrices are as follows. So these are our unknowns. We are to calculate. So if we are coming to picture where left and right boundary conditions contributions always there in the matrix. So finally we get the equation in the matrix form. This is the equation, ith equation. So now we can see this matrix A, HI. So where I is more than 1, 2 up to so on. These matrices are invertible matrices. Two matrices are invertible. Two matrices are invertible matrices. So now what we do is, so you can express Z1 minus 1 as in this form because it is a invertible matrix. So we can use the bracket and we can express Z minus. So similarly, you substitute this Z minus 1 into previous equation and you eliminate. So when you go to equation number 14 and from this you can condense the equation systematically. So when you go to the condensed equations are of the form, this is the condensed equation of the form. So it is up to 1 is equal to 1 comma 2 up to 1 smaller. So similarly at the interface, you can also find the similar equation. You find the equation of this form. So this is the equation of the conventional form of the interface. So where gamma delta L, okay, this is the equation. So now the smaller system after convincing, so we will get a system of 2n plus 2 size. Earlier it was the 4n plus 4 plus 2. As I have seen, so we have 4n plus 2, so we have brought it to smallest size of 2 of this form. So without using any information, we are convincing the system in a smaller system. So this is again results ABD structure almost block diagonal system. So here you can see these are not entries, gamma 1. These are 2 by 2 matrices. These are 2 by 2 matrices. Gamma 1 is 2 by 2, I2 is 2 by 2 matrices. This is the block structure, but in the block structure, each entry is a matrix. Each entry is a matrix. That is the reason it's almost block diagonal matrix. So now the question is how do we solve efficiently? You cannot solve by using Gauss elimination method. So as you know, if you have a tri-diagonal system, and if you use the Gauss elimination method, that consumes a lot of memory. So generally people, if you come across a tri-diagonal system, people use the Gauss algorithm to solve efficiently. The reason is if you use the Gauss elimination method, so in the Gauss elimination method, so again, okay, you have tri-diagonal system only 3 diagonals are non-zero, so rest of these are these remaining inputs of zeros. These are inputs of zeros. Suppose if you use the Gauss elimination method to find the solution, so what is going to happen is that these zeros will be replaced by non-zero entries. So use what you will be using element row operations. So using the element row operation, sometimes these zeros will be replaced by non-zero entries. So you require number of operations, more number of operations. So to avoid this, people use Thomas algorithm that exactly, so wherever 0 entries required, but only make 0 entries. So if it is all the 0 entries, it will be provided 0 entries only. So that is the Thomas algorithm for tri-diagonal system. Second here, so we will not use the Gauss elimination method. So in the literature there are many ready-made solvers, that is the proton solvers are there, 3 OPC softwares. So there are Karnatak and other softwares. So what we do is, so we have built our own natural version of ABD solver. So we have built our own solver and we found a system at the cost of other n-square operations. This is a very effective solver. And suppose if you have interface conditions U and its fluxes are different of the interface, so there are continuity equations you can modify accordingly. So without effectively structure. As we have seen here, so this is only you need to handle carefully. It won't change much. This it won't change much, okay? So this is from coming from interface, this is coming from interface. So I'll show you one example. So the first example is so when the derivative minus beta of x into Ax, x is equal to 0. So this is example is taken from this. So it's initial condition and the normal conditions and the interface beta of x is a piece constant. And if you apply, this is the interface, this is the interface conditions and the interface, and the exact solution is exact solution. And you can say the beta 1 is equal to 1, beta 2 is equal to 1 upon 25. So we get the number of participants is 20, 40, 60, 80 up to so. So these are the infinite negative, so infinite factor. Okay, these are the errors and these are the other convergence. You can see the other convergence we get to 4th order convergence. So which is expected we are using a qubit polynomial. So the cubic parallel, the optimal is 4,000 conversions. Because we have this derivative here. So generally, it will go 1 less, okay, if the derivative means it will go 500 conversions, but still we achieve 4,000 accuracy. This is the super convergence phenomenon. So this orthogonal frame classification method, so this super convergence phenomenon is the observed. Similarly, the other ANT or actual errors, you can see these are also optimal convergence. So this is the interface solution. So we go to another example. So this example is taken from this. We take this from this chapter. So where the topics is feature continuous. So we have initial condition and the boundary conditions. We have interface condition and the exhaust condition is known well. So then again we perform numerics. So we get beta 1 is equal to 1 plus 6 for beta 2, 1 plus x minus 1 upon 4 whole square. So we get again 4 of this. So this is the graphical solution. So now we have seen, I have given few examples, and so those are literature, we can look at our paper and show at the end inference. So now I have to take another interface problem. So this is over because I may be running the so we consider two-dimensional initial and boundary problem. So variable dot is equal to grad dot alpha time grad u plus f of x comma y comma t. So x comma y belongs to omega, t belongs to incremental 0 comma capital T quantity. The Cashner condition and the boundary conditions where our to be is going to be the curve are at the boundary condition. These operator. These operator. So the problem has a vertical interface now. Now we are one-dimensional. Now we are in two-dimensional. So this is my x-axis. This is my y-axis. So I think you will be discussing like this. So now here the interface is vertical interface or horizontal interface. Or you can also consider even diagonal interface also. So any interface, so whether it is horizontal, vertical or diagonal. But I am not discussing the interface of this sort, like a curved interface. Interface are not discussed. So current interface we have approximately talking is bit channel. For this method bit channel. So I'm not allowing current interface, I'm allowing only horizontal, vertical and diagonal. So here for convenience I'm taking vertical interface. So these are the interface conditions. And alpha is a T-space constant. So alpha in this region and alpha in this region. So when alpha is not equal to, this is a flux of conditions. This is a flux condition of the interface. So what are the applications? So the one application is the continuous casting in the metallurgical industry. The second application is the freezing process of perishable food shops in food engineering. The application is the magnetic flow hyperthermal feed mechanism. So some of the applications where the two-dimensional collaborative interface solvers appears. So many others attempted such problems some of the papers, some of the others are listed here. Whatever methods you can, they are usually an alternative direction, both fluid method. So in this paper, we are using match with Krishna Rajpur ADL method in the 50th paper. Similarly, multi-scale method in the 6th paper. So, we are going to the abdominal cell collocation method in this two-dimensional parabolic interface problem. We apply ADL triangle method. So why this ADL triangle advanced cell collocation method? As I mentioned by previous slides, it gives super convergence results and we can handle all types of interfaces under boundary conditions efficiently. So now we require function source we can define n3 minus 1 4. So phi such that phi belongs to piecewise continuous functions in the interval 0, 1. So we have taken a unit set and so phi restricted to each interval is a cubic polynomial. So then these are the basic functions. And so this is a M31. Since superscript chart for polynomial degree, subscript chart for continuity. Okay. So phi belongs to C1 function. And psi is restricted to each interval is a cubic polynomial. So in this we can take basic functions in this form. The cubic basic functions we take. So we have a vertical interface. Okay? So vertical interface. So we choose. So here okay, we have a difficulty here, okay? One direction is we can use Hermite cubics, another direction we use this is mononomial basis functions. So again we have this super most usually quantities of points we use to get the photo accuracy. And we apply ADL rank advanced location method. It is a two-step procedure. So this is one step gives this equation, another step gives another this equation. So we have f k plus half is the so 1/2 f k plus 1 is the term line plus f k term. So now I can say if you add these two equations, so you get this equation. If you subtract this equation, these two equations, you get this equation. So now what to do is, so you this equation you substitute here and simplify. So you get this equation. You get this equation. So now we integrate uk plus 1 is equal to uk plus 1 minus uk, then we write this equation. So now, since we are in a finite dimensional problem, so we use, since we know algebra, we approximate by a finite linear combination of basis functions. So this is one basis function, this is another basis function. So the solution we approximate as a finite linear combination basis functions. If you apply, so we get a section of values. So this linear system. So this is a conical matrix solid. Interpolate V1 to the power B2 plus delta T upon P, A1 to the power B2 up to swap. So matrices A1, A2, B1, B2 given in this. So if we can write it this one, so we can put it in this. Where I is the identity matrix of, where I is the unit matrix of any matrix, unit matrix, all ones. So if you, so when we can calculate, we can calculate the solving in these two steps. So first you solve this equation. So okay, okay, plus one, put it here, then okay. Finally get it. So here's an example. So I'm extending my term, so I will give example. So this example is taken in this server. So this is approximation and this is the initial condition and the boundary conditions are given. So this is the interface of XL is 1/2. So this is the first function, yes, we can calculate for the equation. So we have element matrix for U, UI, and UX. So this is how we can get the practice we get. So this gives you typical margins per number. So similarly, the several amounts, any creative action, we can eliminate. And yes, come up with six. Again, I get document. So, let's say, when we elaborate interface column, to get elaborate interface column, how to apply organized collection methods, and I've shown some examples. I will show you some examples. So those who are interested, more details, they can contact me or they can go to our papers. So this is the recently published paper. So you can all, this is one, two, these are all our papers, you can go through. So this also, so some of the literature if you want about advanced organizations, we can go through. These papers. So thank you for your attention. If you have any questions, you can ask.
Thank you. Audience, any questions? Any questions from your side? Please raise it. No questions? Thank you, Dhananjay sir. Have given good lecture.
Any questions?
I think no response from audience side. But am I audible? Any questions, please? Dhananjay sir, am I audible? Hello?
Sir?
Am I audible, sir?
Yes, please,
Yeah.
please.
Audience for young researchers, if you have any questions, you please raise it because it is a wonderful basic lecture on collocation methods and finite difference method. Sir is also taking some examples how to solve the methods. So if you have any doubts, you please raise it. No doubts? Thank you, Dhananjay sir. I think there is no doubts means your lecture is
Thank you very much.
the lecture is understood by everybody. And it is very good explanation, sir. I have some doubts regarding the collocation methods. All the doubts are clarified because you go for the in-depth and the basics. So wonderful lecture, sir. Thank you so much.
Thank you, sir. Thank you.
Bye, sir. Thank you. given by Dr. K. Padmanabh Reddy, Assistant Professor, Department of Mathematics, Vijayanagara Sri Krishnadevara University, Ballari. Sir has completed his PhD from Karnataka University, Dharwad. The title of the thesis is in wavelet analysis and its applications in wavelet analysis and its applications. Research guide of Padmanabh Reddy sir is Dr. V.A. Hiramat, and research co-guide of sir is Professor N.M. Burjike. Mr. Reddy produced 36 publications, and his area of interest is wavelets, numerical analysis, differential equations, and mathematical imaging. Professor Reddy has a 15 years of teaching experience and also having a enriched research area and research projects. He completed one project. The title of the project is Wavelets and Their Scientific Computing, supported by Vision Group of Science and Technology, Government of Karnataka, during the year 2016 and 17. Padmanabh Reddy sir won the Infosys Cash Prize for securing highest percentage in mathematics for the period of 1999 and 2002. Now I am nominating Professor A. Padmanabh Reddy garu to the stage and give his wonderful lectures.
I thank today's session chaired by the Professor K. Maruti Prasad sir for your kind words about my introduction, and I also thank organizers of this conference, especially teaching faculty and non-teaching staff of the mathematics department, for giving me an opportunity to share my knowledge in front of this in this hall. So now I will start my talk. So I have given my talk title was in this Weierstrass approximation theory to universal approximation of wavelets, but I am just concentrating more on R wavelets. So I will orally touch the history. Okay. Now I will be concentrating more on R wavelets. It is very easy to understand, and I am using three very important inequalities and definitions. I will be exploiting those and how they are helpful to derive more bounds on the wavelet coefficients. Okay. Okay. Sure. Approximation theory plays an important role in pure or applied mathematics. For example, very simple thing is that for understanding root 2, it is a irrational number, but while calculations, root 2 cannot be considered. So for that case, we have to give certain approximation to the root 2. There are the following like this. Root 2 can be written is approximated by 1.4. It is approximated for up to 1 decimal place. Next 1.41. Next 1.414 like that. We are going to add more and more decimal places. Then only we are going to get better approximations. This is a very simple one to understand. Next, there are number of celebrated theorems in analysis. One of the theorems is nothing but Weierstrass approximation theorem. Any guess about the what might be the statement? Any guess? Weierstrass says that you give me a continuous function of your desired threshold called as a epsilon, then I will return to you a polynomial of certain degree, say Pn. So the error is within the epsilon tube. within the epsilon tube. That means if you take a tube, a tube centered at your function f of x, then that just like this one, f of x is continuous, especially it is defined only on for compact sets. Later, Hausdorff spaces was denoted by with extended by Stone. That is called Stone-Weierstrass theorem. But just I am concentrating only on Weierstrass theorem. So f is continuous like this, and epsilon is of your accuracy, means you are interested to allowing that error. He is going to produce an epsilon tube, means a tube centered at this function. This is epsilon by 2, but the total length is epsilon. He will produce a polynomial Pn. It lies in this tube. So this is the one of the celebrated theorem called Weierstrass approximation theorem. Any continuous function can be approximated by an arbitrary polynomial. That arbitrary polynomial depends upon your epsilon. So, and majority, why this is true? Because set of all polynomials are dense in continuous functions. That is the behind story. Next, once f is continuous, the problem is that Pn is a polynomial of degree higher. Okay, when epsilon is small, n is high. This is inversely proportional. Whenever if you want less error, polynomial degree must be high. So, but he is silent about how to construct. Later, Bernstein and other mathematicians, they have produced called Bernstein polynomial. He is giving how to construct that polynomial. Okay, that is one story. Next, later, Taylor polynomial. Okay, Taylor polynomial is, it requires function must be having more number of derivatives. Suppose a function which do not have much derivatives, that theorem cannot be used for our purpose. Okay, these are all certain limitations. Next, we will is just like next another these are all story about approximation theorems. First one is, I am not interested in enumeration. Just randomly, Weierstrass approximation theorem, Taylor approximation theorem, how to construct Bernstein polynomials and learn. Next, immediate one is, whenever f is not continuous, these theorems cannot be applied. We need all the, whatever the occurs in the real world, they are not necessarily continuous. Suppose periodic function, then we can approximate that function by any guess? Whenever f is periodic, we can approximate that function by any guess? Sorry? Fourier, what are those Fourier series? When do you say a series is Fourier series? When do you say a series is Fourier series? Series means just summation of sequence of terms. This is series. Means whenever f is periodic, it can be approximated by a summation of sines and cosines. Sines and cosines. Sines and this is called Fourier series. Okay. What are the limitations of the Fourier series? Limitations of the Fourier series can be studied under the title of Gibbs phenomena. What it says? Let me have this one. Whenever, suppose a function is like this, it is continuous, like, it's not necessarily continuous, because Fourier series is not necessarily continuous. Okay. It must be periodic. It has to be repeated. It has to be repeated. Okay. At the point of discontinuities, it is not possible to approximate by Fourier series exactly, loosely speaking. Okay, this is called Gibbs phenomena. That is follows from the Heisenberg uncertain principle. I am not going into the depth. Okay. So it is on certain limitation can be studied more with the concept of Gibbs phenomena. I am calling approximation theorems what are the positives and where they are having certain everything, whatever the concepts in mathematics, they are having certain hypothesis, means with that only hypothesis, certain conclusion. That's all. Okay, good. Once Gibbs phenomenon is over, so next, why the point of discount is more tiles will occur. More tiles will occur because of the fact that sin x and cos x are never vanish on R. What is the meaning of this one? If you plot sin x function, I am starting from the whenever x is positive, okay. You do same thing like this. On R, sin x never vanish. Similarly, cos x. If by looking at the sin x and cos x, they are never vanishing. Okay. Because of that reason, because we are approximating f of x by terms of sin x and cos x. Because of the sines and cos, then they are not vanishing over R. Due to that reason, we are going to get more tiles. These tiles will not allow for the better approximation. So we want to avoid this one. Means we need how to avoid means just it will give one information that you better choose functions. They are going to be vanished after certain stage. After certain stage means over a set. So that is called we are needing concept called this one compact support. Compact support. So I will define what means by compact support. Okay. Suppose f is function compact support of F, it is nothing but closure of a set A, where F closure support means outside this one. Just call this one as C. Outside C, F vanish. Outside C, F vanish. I will illustrate one example. Okay. Best example is characteristic function. You take any, because we are interested in compact sets. Cat function, how it is different? Any guess? Characteristic function means this is x, whenever x is in closed interval 0, 1, this is 1, 0 otherwise. Okay, means what is the graph looks like? 0 to 1, 1 and remaining all are 0. So these are the functions having compact support, characteristic functions over a compact set. Okay, so these are having not necessarily a domain, not necessarily a compact set. Okay, because we are considering the closure. So this is the best example for compact support functions. Under more general functions, we are interested called wavelets. So, any guess what meant by definition? When do you say a function will be called as a wavelet? Because in mathematics, whatever branch of mathematics, we are always dealing with sets and functions. Without this concept, we can't understand anything about the mathematics. Anything, it will drop to the concept of sets and functions. Okay. Any guess? Wavelet? So a function means just, it is live inside a small interval and vanish outside it. It is having smaller compact support. It is having small compact support. After this one, it is going to be vanish, and it has to form a basis for Hilbert space L to R. Under condition L2. Okay, good. Another thing, it must area is 0. Area means function. Integration is 0. These are the three characteristics one can understand. A function is said to be a wavelet. First thing is, loosely speaking, first one is it is going to be live inside small interval, outside it 0. Next, it has a form, translates and dilations together form a basis for L to R. Another one is its integration is 0. So best example is divide unit interval into two parts and call this one as any dilation, and it is -1. And if we integrate, this is going to be the integration is 0, and it is going to live inside small interval and 0 outside this interval. And dilations and translations form a basis for whole L to R. You complete the whole real line, we are going to get all the this one wavelets. Just shift it. Okay. And dilation means you can bring down and up. Height can be arranged. Okay. Good. So now these are all the Haar wavelets. Now I will going to study about what are the properties of Haar wavelets, because this is going to be a prototype other family of wavelets. So other family means we are considering a family of wavelets called Dabochi wavelets, and what is the very interesting is Haar wavelet. It is a very prototype for other all families of wavelets. So my talk is like this: introduction, sharper bonds for Haar wavelet coefficients, results and discussion, conclusion and future work, and reference. So as like routine. Okay, next. Haar wavelet is the only wavelet family with an explicit expression. Means explicit expression means like this. Okay. There are explicit and implicit. Okay. Continuous irangala. ಕಾಣಿಸಂಗಲ್ಲ ಕಾಣಿಸುತ್ತೆ ಇಲ್ಲಿ ಇಲ್ಲಿ ಓಕೆ explicit expression means psi of x is 1 when x is 0 to 1 by 2, minus 1, x is 1 by 2 to 1, 0 otherwise. This is called explicit expression. This is called explicit expression. Other families of wavelets are there, they do not have explicit expression. This is the only wavelet among the Dabochi's families having the explicit expression. Okay. Next. And not only this one, it is having the smaller compact support among other families of wavelets. Now this is like this, what we have considered now, phi of t. Good. Next slide. Just like what any function, square integrable function, then it has the following representation. I can represent in like this. Here coefficients S00 and all these coefficients are called Haar scaling and wavelet coefficients. So these are all orthonormal basis. Is a vector space. Suppose V is a vector space having orthonormal basis. Say I will be considering only 3 dimension because I want to change this concept to the. So V1, V2, V3, B orthonormal basis for V. Now, if you consider any vector alpha in V, then this alpha can be written as linear combination of these vectors. So, what way it is going to be helpful orthonormal with distinct from just basis? Any guess? What is the advantage having orthonormal basis compared to just basis? Here the thing is that you can easily calculate these coefficients very easily compared to the just ordinary basis. This C1 is nothing but this C1, because I am assuming orthonormal basis. This C1, it is nothing but inner product of alpha with V1. This C2, it is nothing but inner product of alpha and V2. And this C3, it is nothing but inner product of alpha and V3. Okay, this is the advantage of having orthonormal basis. So when it is continuous, that inner product is f and g, it is nothing but this integral of f of x into g of x, its complex conjugate into dx. It is giving statistical terms how f and g are correlated. Whenever I am choosing g as a wavelet, inner product of a function with respect to a wavelet, it will give me a coefficient because they are the orthonormal. These coefficients will give me an information about with this wavelet what is the correlation for a given f. So coefficients plays an important role to understand a function because it will give the correlation of the with respect to the wavelet. So this is the just now. This is f and these are the g. G is a function. Okay. This will give the this coefficient S00 will give me a just a integration. djk will give me a what djk will give me a direct information that what is the correlation between f and psi j. This correlation will help me to understand more. Okay, good. Next. So this is the djk, just like f of x, g of x, and I know that g is having compact support, means inside an interval it will live, otherwise it is going to be vanish. What is the interval which is going to be live is k by 2 power j to k plus 1 by 2 power j. That interval is divided into two equal parts. In that first equal part plus 1, in second equal part minus 1. Because of that reason it is going to be minus. Okay. And this, I want to estimate what is the correlation. The very interesting inequality, everybody know, those who have studied about the inner product space. Very interesting inequality. Suppose I am having IPS, inner product space, means it is equipped with inner product. This correlation between f and g in statistical terms, because we want to exploit the properties of coefficients. I want to estimate how much big. Any guess? Just inner product space, f and g. It is nothing but, it cannot exceed, means its inner product of absolute value, it cannot exceed the product of their individual norms. It cannot exceed product of their individual. This is nothing but any name for this one. What is this inequality is called? This is called Cauchy-Schwarz inequality. I am using Cauchy-Schwarz inequality to exploit the coefficient upper bound. Okay. This is nothing but norm of f. Next, norm of g. G is the wavelet. Because plus 1 and minus 1, that allow me to, what is the length of that interval? 2 power j. That is 2 power j by 2. Okay, good. Because another why this is one factor is there like this. So next, this is a one bound. My intention is to better better sharper bounds. Now this is a very rough bound. Cauchy's square inequality will give me to estimate a rough bound. Next, in the literature, a Majak and others, they have given another bound. They have assumed that f is differentiable. F dash exists. Whenever f dash exists, that same wavelet quotient has another bound. It is nothing but eta by 2 power j plus 1. Means this djk is having another bound, eta power 2 power j plus 1, where eta is upper bound of f dash. This can be derived by using Lagrange mean value theorem. Lagrange mean value theorem is applied to estimate that one. So this is, I am having two bounds in the literature. And open interval AB, then f of x minus f of y divided by x minus y equals to f dash of eta, where eta is any number in the open interval x and y. That theorem. Okay. Now, so is there another bound? Can I estimate? So oscillation of a function does not need differentiability of f. Oscillation of a function does not need differentiability of f. Oscillation of function just needs a bounded variation. So this is the definition. What is the oscillation of a bounded function f on closed interval? Is a supremum of the set mod of f of t1 minus f of t2, where t1 and t2 are allowed over the closed interval AB. They may be any two numbers of numbers and is denoted by W. W stands for the oscillation, like that. Okay. Okay, this is the theorem, and so what I am assuming that f is a continuous function. Whenever f is continuous, these are all the bounds djk. Okay, Cauchy squares, Majak bounds, and these are the bounds derived by me. All these oscillations. Okay, mod of djk cannot exceed oscillation of a function over that smaller interval. Okay, so this is the terminologies mjk, small mjk, m dash jk, and those are all the small notations used for the defining the oscillation of a function. Next, this is the proof. Okay, so I am using oscillation of a function and mean value theorem for deriving this. Next. Okay, good. Next. So what was my aim is that obtain better bounds, obtain sharper bounds, and I have it in the form of, so what corollary? Corollary 1 meets the goal of this study or article, whatever it means. In the next section, we are concentrating on these bounds. So here we have derived sharper bounds. It is better than the whatever the existing in the literature. Okay, good. So now I am considering some numerical experiments for conducting sharper bounds. Okay. So this is a simple function I am considering is exponential on closed interval 0, 1. Since e power x is monotone, parameter appears in the various bounds are easy to compute. Because monotone means it is left hand point is the supremum where it attains, infimum, right hand point is going to be the supremum. It is easy to calculate. So based on this, these are obtained bounds proposed, and these are the coefficients actually calculated, and these are the upper bounds obtained, and this is the Cauchy square inequality, and this is the Majak bounds. Okay, because e power x is differentiable and bounded, it cannot. So it is going to be according to the Cauchy square inequality. So one bound is 1.7873, according to Majak 1.35, but actual bound one can is 0.8591. If you compare among these three numbers, what are those? 1.7873, 1.3591, 0.8591. Which one is the least? So that is the better bond. Okay, that is the better bond. Just like both can be a layman words I am putting. Suppose a person you don't know Karnatak University campus. You know little bit. If I will pose one question to him. How much distance from this one CBT, Central Bus Stand of Dharwad, to the university? You know little bit. What might be? He will be the maybe less than or equals to 10 kilometers. That is also correct or not? Yes. Suppose some person, you know something, he roamed around twice or thrice. Then he will show not so much, maybe less than or equals to 8. That is also correct answer. But I would roam number of times. I will say that around exactly 6 to 7 kilometers. It's greater than 6, I think. Okay, 6 to 7. So which one is the better bound? Yes. Okay, it has to close. It has to close it. Okay, good. But 3 are correct answers. 3 are correct answers. Which one is the better? Okay, good. Next. So these are all other things, same thing. Okay, next again. So this is means I have constructed one function. This cannot be implemented. This cannot be implemented by the Majak bounds because this function is not differentiable. This function is not different. Majak bounds can be obtained only for differentiable bounded function. This is a function which cannot be, which is not differentiable, and hence it does not meet the hypothesis of the research article published by Majak. So then, next part it is applicable for my proposed hypothesis. Okay. Next, let us truncate the sigma function. So this is the sigma function. Okay. Now, so what? Whenever f is continuous, whenever the high resolution compact support is going to be very small. Whenever compact support is very small, so I am going to get a small coefficient. That small, whenever coefficients are very small, then that correlation is very less. Whenever big, we need a correlation very close to 1. Okay. Okay, good. Next. So this is, look at the second graph. These are all I have drawn Haar wavelet coefficients. These are all Haar wavelet coefficients. So there is an abrupt change here. There is an abrupt change compared to other coefficients. It indicates something. So this is the one of the applications of my contribution. If you draw the wavelet coefficient, wherever abrupt changes are there, it indicates something. So now, just these two plots are same. Just I have zoomed in this part. That's all. I have zoomed in this part and kept here. All wavelet coefficients are lies within the small tube. All wavelet coefficients are lies within a small tube. But it suddenly in the vicinity of 150, maybe it is written something there. In this vicinity, it jumped compared to the tube. Okay. So what it indicates? Whenever the abrupt changes in the coefficients, so what is my assumption? F is continuous. Means abrupt changes means it is contradicts. F is not continuous at that point. F is not continuous. So Haar wavelets, what it will say that it will show that it is not continuous at a certain point. Nothing. What is the Heisenberg principle? Speed and momentum. I'm not wrong. Cannot be simultaneously measured. Same thing. Where is the discontinuity cannot be measured exactly. But over a small interval, I can say that F is discontinuous. Whenever interval is very, very, very small, it is going to be the very good contribution. But among all other wavelets, the small interval can be achieved only by Haar wavelets. That is the reason that I am not consider other wavelets. Because I want to locate discontinuities at which point is not possible, but in a small closed interval, I can say that discontinuities lies. That is my achievement. Okay. Good. Next. So what is that interval size? In that interval, 130 by 512, 134 by 512, in that interval, F is discontinuous. And this interval length is very small. Okay. Whenever interval length is very small, better achievement. Okay. Next. Okay, this is the conclusion. We derived the expressions for lower and upper bounds for each Harvey-Late quotient djk, and further we have shown that its absolute value is less than or equal to half of the oscillation underlying continuous function, that is compact support, and such oscillation based or bound is sharper than bound existing in the literature, and the same is concluded, validated in the Karnatak one, and we have achieved that one. Okay. First two test example respectively. Further, a larger hard detail coefficient has insights, means abrupt changes. That is termed as a larger coefficient absolute. It has insights. What are those insights? Whenever the detail coefficient is significantly larger compared to its neighbor, it indicates that it indicates that the considered function has discontinuities in that interval of length 1 by 2 power j. I am going to give a interval where f is discontinuous. That interval length is 1 by 2 power j. Whenever j increases, that length of the interval decreases. Okay. Good. Last two examples are the testimony to the discussed insight and hence application of derived inequalities. So designed bounds plays a crucial role in approximating the threshold value at each level. Once we know the threshold value at each and it has applications not only locating wavelet based preconditioners. So that is that was my research. Okay, it will meet that part also. Next. So these are all my references. Okay. So I have his 11th references is from my senior and organizer of one of the organizers for this conference, S.C. Siraj Sethi sir, and his student S. Kumpinar sir reference paper. Okay. That is a very nice paper. Okay, thank you. So next, only one thing, universal approximation theorem. What it says? Universal approach. Any function can be approximated by a neural network. That is very advanced concept. I will not touch that one. If you are willing, then I will touch. Otherwise, I will not. Okay. Any continuous, not only continuous, any function can be approximated by a neural network. Okay. That is a universal. So now Weierstrass approximation theorem, Bernstein polynomial, next Fourier series, next Gibbs phenomena, wavelets. Why only R wavelets I have considered? This is the universal approximation. Okay, thank you. If any questions, I will be happy to address.
Any questions from the audience?
No questions. I really appreciated, sir, your wonderful lecture. I think converting for my biofluid dynamics, because it is wavelets are very useful in blood flow phenomena. So some doubts, I think I get it as clarified now. So really wonderful lecture, sir. It is more useful for the researchers. Thank you, sir. Thank you for giving a nice lecture.
I thank organizers for giving an opportunity.